Hello friends, welcome to lecture 3 of EMT. Here we're going to discuss about displacement current and displacement current density, right? So before we start, please subscribe the channel, hit the thumbs up button. If you are new to my channel, subscribe the channel and share it with your friends and help me to grow my channel and inspire me to create new contents for you. So now let's start. Now, according to Ampere's law, suppose if we have a conductor, this is a conductor, suppose, and the current through this conductor is, suppose, I. Current carried by this conductor is, suppose, I. And if you assume a close, suppose we have a close curved here. Now you see we have a closed loop here, so area enclosed by it, this area, you see, so current through this area is now I, right? So according to Ampere's law, we get line integral B dot dl is equal to mu naught I. That's what we get, right? Mu naught I. So now you see this mu naught I, also it can be also written as mu naught integration J, that is current density, ds. This formula is correct for only this conduction current, steady current. This is steady current. That means this current is not changing with time, right? This is correct for steady current. Now you see, let us take a situation here. Suppose we have a capacitor, this parallel plate capacitor, okay, and this is source, right? Positive terminal, negative terminal, and current flows through this is, suppose, I again, right? So let me use small I here, as I have written small I in the diagram. So now you see, so as this plate is connected to the positive terminal, that is why it will be positively charged, and charge will be increasing on it with time. Similarly, this one will be negatively charged, right? So with time there will be change in charge, right? Amount of charge on both plates, okay. Due to that, here you see these two plates are not connected, these two are not connected, so between them there should not be any current, right? Now you see, if you keep a magnetic here, if you keep a compass between them, right here, if you keep a compass between them, then the needle of the compass, magnetic needle of it, will show deflection. So if it shows deflection, then there must be a magnetic field, and if there is magnetic field, though there is no magnet, then there must be a current, right? There must be electric field as well, because now you see that Oersted shows that when you bring a compass, or if you bring a magnetic needle near a conductor, and when current uh, flows through this, it shows deflections, right? So here you see, as you will keep a compass here, it will show deflection, right? Because of the change in there will be an electric field, okay, uh, which creates a magnetic field as well. And if there is electric field, means there must be some kind of current. So that current we used to say displacement current, small id, right? So here you see, let me clean this part. So this formula given by Ampere was modified by Maxwell's. So he said that there must be another term, that is you know uh, line integral B dot dl mu naught surface integral J plus, that is current density, epsilon naught del E by del T ds. Okay, so he modified that way, right? And here you see this J is nothing but current density, right? And here we will get another term, this one, this is epsilon, this is epsilon naught, this is called displacement current density. Displacement current density. Displacement current density. So we used to represent this by ZD, suppose, that is epsilon naught, this one, right? And as and you see this is this, when we write only J here, this is conduction current density, okay, and this I is conduction current, right? So here one more thing here you see, when I have discussed this, I have explained this in the first lecture also, but there I have made a mistake. I had written ZD is equal to J plus epsilon naught del E by del T. So if you have taken the note from there, then make a correction here, cut the J, okay, just write this term only, okay. So hope you have understood this. So now you see, let me clean this, right? So this is called displacement current density, and you know current, displacement current will be given by surface integral of JD ds, right? And that will be equal to del phi epsilon naught del phi by del T. So del phi by del T, because here you see phi is nothing but E dot ds, surface integral this, right? And as J D, here you see this ZD will be equal to epsilon naught del this one by this, right? So if you take the surface integral of, let me scroll down, okay. So then here you see, if you take the surface integral of this, then integration epsilon naught del E by del T, right, ds, you can write that way. And this is also can be written as epsilon naught partial derivative of surface integration E dot ds, right? You can write that way. This is surface integral, and this is your phi, that is magnetic flux, sorry, electric flux, not magnetic flux, electric flux, phi, right? And this is del phi by del T represents change in this represents change in rate of change of you can write rate of change of electric flux, rate of change of electric flux. This term, right? And when you multiply epsilon naught, it becomes current, displacement current, right? This whole term is known as displacement current. So displacement current arises due to displacement current arise due to the change in electric flux, right? So here this is displacement current, right? Displacement current. So we can say that displacement current is the current arises from the variation of electric field with time. Electric field with time, right? So hope you have understood this. So thank you for watching. See you in the next video. Please share with your friends, subscribe the channel, hit the thumbs up button, hit the bell icon also, so that you get notified when new video will be uploaded.